Hello everyone. I have to redo the first video about the design of the reinforcement bars because I forgot to show you the actual beam where the reinforcement we're gonna be designing. Okay, here's the continuous beam that we're gonna be designing the reinforcement using the structural programming that I created. The beam has two spans, 6 meter each. This is the beam from the apartment building. This is cantilever right here is the balcony of the apartment. And I assume that you know how to do your moment distribution, and the maximum moment for this particular continuous beam, this beam is considered to be continuous. Alright, the maximum moment is 11 right here, 1171.08 kilonewton meter. This is the reinforcements that we're going to be designing. This is the bottom bar and this is the top bar. In this case, in this particular continuous beam, the maximum moment occurred at the midspan of the beam. So therefore, the portion of the beam, the negative moment right here, is smaller than the maximum moment right here at the midspan. So therefore, the design of the top bars as well will be designed the same as the bottom bar. In most cases, in my experience, the portion of the beam, the intersection between the column and the beam right here, in most cases the moment here is greater than the moment occurred at the midspan of the beam. So but this continuous beam, we have only one maximum moment to design the reinforcement bars, both the bottom bar, this one, and the top bar, this one. Usually top bars has more bars there. This is the positive moment right here that you're designing, and the negative moment in your moment distribution represents the area of intersection between the column and the beam right here. Usually there are more bars in there. The maximum moment there is greater than the maximum moment positive moment right here. So but in this case we only have one maximum moment, which is 11.71.08, and that is the moment that we're going to be using to design all these bars here. See, this is 28 millimeter diameter bar. We don't know how many bars we're gonna end up to. Well, let's find out how many. The size of the beam is 800 by 400 millimeter. I'm just gonna have to change stirrups right here. This stirrups is yellow. I can't see it. I'll change it to blue. There we go. The distance is the stirrup is 10 millimeter diameter with a distance of 0.10 on center. right, all the way the same. I designed it like the same, although by theory the stirrups here should have a farther distance than this 10.10 on center, but to make it easy I design all the same distances. Now let's go to design this reinforcement bars right here, all of them. This is the top bars, this is the bottom bars, and they're all the same sizes. It's 28 millimeter diameter. We're gonna use that. And the concrete that I use, strength of the concrete that I used here is 35 MPa, and the strength of the steel is 413.7 MPa. So okay, now let's go and find out how many reinforcement bars we're going to use based on the maximum moment that we have here, 11.71.0. and here I want to point out this bar here. These are continuous bar, both top and the bottom. These are the bars where you attach all these stirrups. These are the horizontal bar that runs from one end to the other end, where you can install all the stirrups here. This bar is 16 millimeter in diameter, and I installed 3 bars in there. 3 16 millimeter diameter bars. This is the bottom and the top and the bottom bar where the for the stirrups. Alright, so I'm gonna change this as well. And this is 3 16 millimeter diameter stirrups. Okay. Down there, the 16 millimeter stirrups, the top and the bottom. A bar for the stirrups. These are the bars that continues from one end to the other end. This part here is the wall. This is the balcony of the apartment building, and the span is 6 meters. Alright, now go to design the reinforcement bar. Using the program is going to be quick. Anyways, right here, and the other computer, I use different computer in different programs. This is the other computer where the drawing is, the AutoCAD, and for my architecture and for my engineering is this one here, programming. Okay, now the first prompts from the program is asking you to enter the strength of your specified strength of concrete. Here are the specification data in here. If C is 35 MPa, FY is 413.7 MPa. The width of the beam is 400 millimeter, 0.4, and the depth of the beam is 800 millimeter, which is 0.8 in meter. The bar diameter we're going to use is 28 millimeter. 28 millimeter is 1 inch. Okay. Okay. Now what's is enter this. You're gonna enter the FC and MPa, which is 35 right here. All right. 35. Now program now is asking for the steel strength is 413.7. Now the source of the moment maximum moment is from the beginning of the video, as I show you, is 1171.08 kilonewton. You don't have to type the kilonewton, it's already here. It's programmed to have a kilonewton meter, right? Now the reduction factor for flexural member like beam is 0.9. You're gonna enter that. Computer is asking you. Now the width of the beam is 400 millimeters. It's asking you in meter right here, so you convert that 400 to meter, which is 0.400. Again, the depth of the beam is 800, so 0.800. I just put 800. Make it nice. And then the diameter of the bar is 28 millimeter. Convert that to meter is 0.028. To convert is divided 1000, right? So that's in meter, and then you hit enter. There we go. The first design that we're doing is the actual design by theory, using the formula for the beam, which is mu is equal to 0.9 FYBD square times the P here is the reinforcement ratio, and then multiply by the equation here inside the bracket right here, and which is 1 minus 0.59 Fy over Fc prime times P. Now what is this equation telling you? Inside the bracket there, it means that this part of the equation will be multiplied with the equation inside here. So this portion of the equation will be here. It's multiplied by 1. So there's 1p there. And then if you multiply this part of the equation to the bracket, to the equation inside the bracket right here, we're gonna have this part of the equation, and at the same time there's 1p here already, the reinforcement ratio, and to multiply that you're gonna have a p square. Alright, so this is the result of, and the resulting equation to that is a quadratic equation. I included here the program of the quadratic equation so you can solve for the p, the reinforcement ratio. This reinforcement ratio and this first attempt of design of reinforcement is by using the theoretical formula for the beam. And to design the reinforcement, you need the reinforcement ratio, which is embedded right here. So as a result, because of this equation here, the resulting equation will be a quadratic equation. You gotta know the quadratic equation as well, how to do it. Alright, so you can find the p, and then after solving for the p, then you have to design, you can use it for the design of reinforcement. So where are we now? Here. So in quadratic equation, there are two results. This is x1 and x2 in algebraic expression. And there are two p's here. If the other p is negative, you gotta use the positive one. So, and since both of these two are positive, you gotta use the smaller value, which is 0.01357 as the reinforcement ratio. Alright, so we have that, and this is by theory. This is the first design by theory. There's another design which is by formula from the A.C.I code. The formula that I'm talking about is the formula for the reinforcement balance ratio. Now, this second design now is by using by formula. This is what I'm talking about. The reinforcement balance ratio formula is 0.85 times the reduction factor. This 85 here is by coincidence. There are two of them. Where's this coming from is because of the whatever strength you use for your concrete. When the concrete strength is more than 25 MPa, you use 0.85. The reduction factor right here could be 0.70, 0.75, 0.65, or 0.9, and usually for the column is 0.70. So for the beam with the concrete strength of more than 25 MPa, use the 0.85 as a reduction factor. So we're gonna enter that here in the formula. Computer now is asking you to enter the reduction factor for the reinforcement balance ratio formula. So enter the 0.85. It's not always 0.85, as I said. It could be 0.70, 0.75. Minimum is 0.65. Alright, so 0.85. That's all we're gonna need for the design of reinforcement valve. The program execute itself. Now the result from the right here this the A.C.I code provision says that it is necessary to not over reinforce the beam by taking the reinforcement ratio P equal to 0.5 P maximum. Alright, the P here using the by theory we found out it's 0.01357. If you round it up, it becomes like 6. Now by formula, the result is almost identical right here. This is the reinforcement balance ratio. Alright, 0.0362 is almost identical. This is a coincidence. The theory versus the formula, usually they don't have a result of the same P balance right here. By formula we get about the same as by the theory right there, right here. Right here, 1357. So the A.C.I code provision, it is necessary to not over reinforce the beam by taking the reinforcement ratio equal to 0.5 P maximum. The P maximum that we're talking about here in this provision here is the P1 right here. And also by formula here, the balance. They are identical. So this is the P maximum. Now according to these provisions here, you have to take it, the maximum that you can take, you can use that is by multiplying it in half. It's 0.5 P max right there. And now you have an option from whether you take it by 0.1 times P max up to maximum 0.5 P max. Now here are the result of the P that usable to design. The 0.2 P max is right here, 0.005. That is the reinforcement ratio that is usable for the design, and then the P3 here is the 0.3 multiplied by P max, and I usually use this. I end up using this. I'm just showing you the breakdown of the options that you're allowed to use. For P2 is way too small. There are 3 bars as a result of using this. I usually 0.5 P maximum, that's it. It's and it has 0.0136. So there are the options for P maximum. The maximum you can use is 0.5 P max. The P max here is the reinforcement balance ratio derived from the formula right here. The formula is 0.85 times 0.85 multiplied by FC over Fy, then multiplied by question there in the bracket 600 divided by close parentheses and open parentheses and close parentheses Fy plus 600. The result of this is this P maximum. And following the A.C.I code, you can use the P maximum half of it, which is 0.5. That's why it's in here. But still, you have an option to multiply it to 0.1 up to 0.5. So usually I end up using this. Depends on how many is the result, how many reinforcement is the result, using 0.5 P maximum right there. Alright, so again, the PB here and the P1, this is by theory and this is by formula, and usually they are identical, so it's good. And then now for 0.5 P max, the result of the design is 7.069. It's more than 7 pieces. I just neglect this after the decimal point here is too small. I consider 7 pieces of 28mm diameter bar, both top and the bottom bars. And for 0.4 P max, so that's why I break this down, so you can look at how many bars of your choice. And by the way, these bars, they're all safe. Okay, if you reverse the design, you have the section and you have the bar, you find the maximum moment that the capacity of the section of your beam, if the capacity is less than 1171.08 maximum moment, if this bar gets that less than that, then this is safe. Even this bar here. So I'm just showing you the option, the breakdown of the option that you can do in designing reinforcement. For 0.5 P max, 7 bars. For 0.4 P max is 5.66. It's like 6 bars. You round it off. When there's an existence here like 0.6, it is considered like 6 bars right here. And for 0.3 P max, 4.2, that is 5. And for it's 0.3, this is 0.3, and this 0.2 P max, you have about 3 bars. This is too small. I usually consider the 0.5 P max. And another important point that you need to be considering here is to avoid using the actual P balance right here. This is the P max. This is the P maximum. You can practice this, use that, and you're gonna have double the numbers of this, about 15 for a beam. For a beam of 400 millimeter wide, it's congested. That's why the ASI code warns this, that you can only use 0.5 of the P maximum. If you use this without multiplying by half, which is 0.5, the reinforcement right here for 0.5 P max will double that. It's like 28 millimeter bar for one beam. Wow, that is over designed, over reinforced. That's why the ASI code has this warning right here, right here. So here again, 0.5 P max 7, 0.4 there's 6, 0.3 is 5, and 0.2 is like 3. Alright, so these are the result of the reinforcement bar design using both. Usually by theory it's different than by formula, so you have to make a decision there, and you have to make sure that the beam is not congested with reinforcement. You don't need to underestimate the strength of the steel. One steel bar can carry a truck, can lift up the truck without giving it. Imagine there are 29,000 pounds strength of 1 inch diameter of bar. Okay, that's the steel reinforcement is the most reliable construction material to be used. Alright, so I think that's all. That's the end of the video, and I hope you guys, right? So we still got to go back to this is the beam. I forgot to show you in the first video, so now I'm gonna have to redo this. This is actually this is 7. It's 728 millimeter diameter bar, right? So we found out that design there. You can use 7, 6, 5, up to 5. You'd be okay. Steel is very strong. You don't have to worry about that. And not only that, there are 3 continuous bar right here. There are 3 continuous bar right here for the stirrups. Right here. So both the bottom bar and the top bar right here, the number of bars there is 7, and the distance of cut off there is L over 4. They're all L over 4 because the span here, they're the same, 6 meters. Alright, so that's the end of the video, and I hope you have everything that you want to find out. The first video doesn't have the actual drawing of the beam. Okay, this is structural drawing. This is the architecture part of me. I have both the architecture and the structural engineering, so I'm just gonna have to find time to upload videos. so that I can help as much as I can, right? And I'm gonna do the quadratic equation programming, so because you're gonna be using quadratic equation, you know, in structural